This is a video walkthrough for the code for an independent samples t-test. So to start off with, we will be using the sleep dataset. It's one of the datasets included in R, and we're assigning it to an object called df. And so we'll do that, and we'll see that it is assigned it down here. Looking over in our environment, we see that under data, we have this thing called df. It's a data frame, and it has 20 observations of 3 variables. If we wanted to see what exactly those 3 variables were, we could look at the head or the top 6 rows, and we see that we have 3 columns, as we would expect, because it says up here we have 3 variables, and they are extra, group, and ID. In reverse order, ID is the patient ID number. Group is which sleep drug the patient received. And extra is how many additional hours of sleep the patient received after taking the sleep drug. So to start, what we'll do is we'll get some descriptive statistics on our data. And we'll be using the psych package to do this. So what we need to do first is call the psych package using the library function. And then we will get the descriptive statistics. And since we want the descriptive statistics by group rather than just as an overall look at our data, we're going to be using the describe by function this time. Pay careful attention to the capitalization. Notice that the B in by is capitalized, and if you don't capitalize it, R will get confused. It won't recognize it as a function, so pay careful attention to the capitalization. Within this function, we say that this is what we would like to be described. So we want the extra column from our data. So here's our data, the $sign saying that it's the extra column that we want. But this time we're adding group, like a group equals argument. And this is saying we'd like the descriptives for this extra column, but we want it grouped by the values in this column. And so we're saying grouping is our data frame and the group column, or remember it's the drug column. So if we do this, we get descriptive statistics by group. And so we see here is for group 1 or drug 1, and here is for group 2 or drug 2. And it provides us with a wide range of information. So it tells us the number of individuals in each group, means, standard deviations, minimum, maximum skew kurtosis, etc. So one of the next things that we might want to do is check for outliers, because we'd really rather there not be any outliers in our data. And so a great way to do this visually anyway is to use a box plot. And so we'll be using, again, ggplot to do this. And so first we need to call ggplot. And this time we're going to generate a box plot. So right here, our first line, the ggplot argument, we're defining our data. So we're saying data equals this df object over here. And then we're defining the aesthetics, or our x and y values. So here we have our x value is our group. So along our x-axis, we want the 2 different groups. And then our y value, or y values, is how much additional sleep was had by each group. So we say y equals extra. We don't have to put this $sign, this df $sign in front of group or extra, because we've already defined where our data is coming from. So we can just put group and extra. Then we have the plus sign, and then we have another row, or another row of code, and we say geom box plot. So this is saying this is the type of graph that we want. We want a box plot, please. It has parentheses. We don't have to put anything in it this time, but you do still have to have the parentheses, so don't forget that. And then we have a plus sign and another line. And this is geom jitter. And what this is going to do is provide individual data points along on our graph. So it'll plot each of the data points so we can see if there are outliers or not. This width equals 0.2 is just saying how spread out width-wise those data points will be. Sometimes if you have a lot of data, you'd want them more spread out so you can visually distinguish dots that might be close to each other. If you don't have a lot of data, you might want it slightly narrower so you can compare it easily. So put your cursor anywhere on this and we can run it, and it'll think for a second before popping up a plot over here. And we can see, here's our plot. Along our x-axis, as we asked for, is our group. So here's drug 1, drug 2. Along the y-axis, as we asked for, is how many hours of extra sleep was obtained by each group, or just obtained. And you can see here's our 0 to reflect the fact that there are negative numbers in our data. And here's the 2 box plots. And what we're looking for specifically is any outliers. So dots that are appearing significantly above or below these tails here. So we can see this one might maybe be a slight outlier, but probably nothing to be terribly concerned about. Perhaps this one as well. And then these are still within these little whiskers, so those would be considered okay. But ultimately, there's no extreme outliers, so there's nothing like all the way down here for this group. So we can consider it something that we can proceed with. The next thing that we'd like to do is check our assumptions. And so we'll check for normality first, and we'll use the Shapiro-Wilk test. And as a reminder, what we did last time with the one sample t-test is we just did Shapiro test, and we said we want that on the trees, the trees data set and the height column. I'm going to need to quickly reassign this data. So if we're in the Shapiro test, it's the exact same thing that we've already gotten, right? But what we can do is we can assign this to an object. So we can say we'd like to assign this test to an object, the SW object here. You can, arbitrary naming. And then it shows up over here. And it says it's a list of 4. The reason that we're going to want to do this, or the reason why we might do this, is because if we look at that, so all you have to do is click it and this will pop up. You can see that, here's this Shapiro-Wilk object. It has this statistic, it has the p-value, the method, and the data name. And so what we can do is we can actually call the statistic and we can call the p-value specifically of this. And so that's what we're going to do because, again, when we're looking at our assumptions, we want our assumptions by group. We're not looking at the assumptions for the data overall. So here we're going to run the Shapiro-Wilk test, but this looks, a little extra as compared to just this one up here. So we're using the tidyverse, so we can use this pipe function. And so we'll go ahead and call that package, and then we'll break this down. So what we're doing first is we're saying, this is our data frame. This is the data we want to use. Please look at this. And this pipe function, so the percent, then the sideways caret, and then the percent, is saying, send our data on to the next line of code. And then here, we are grouping our data. And so we're using the group by function, also from the tidyverse package. And we're saying we'd like it grouped by the drug group, please. So we've sent our data down here and we're saying, please group it by the drug group. and we send it on again. So here's that pipe again. We're sending it on. And this is why we looked at that Shapiro-Wilk object. So we'd like to summarize it. And we're saying this is one of our column names. We're defining it. And we're saying do the Shapiro test on the extra column of our data, because we sent it up here. And what we want in this is the statistic. So that Shapiro statistic, this one right here. This right there. And then we also want a p-value column. And so we're still doing the Shapiro test on our extra column, but what we want to put here is the p-value. So if we run all of this, what we see is we get a table out. So we set, here's our Shapiro-Wilk statistic. That's what's coming out of this row right here. And here's those two values, one for group 1, one for group 2. And then we have a column named p-value, and that is going to be the output of this right here. And so we see for group 1, our p-value is 0.4, which is larger than 0.05, which means that our data are not significantly different from a normal distribution. And then we have for group 2, the p-value is 0.35, again saying that for that group, the data are not significantly different from a normal distribution. So both of our groups, we can say currently, are normally distributed. So that's why we did all of that. We can also visually inspect our data and see if it looks as though it is normally distributed. And to do this, we'd use a histogram. So again, we're using ggplot. Since we already called it up here, we don't have to recall it down here. And we're saying, okay, first line, defining our data. So we'd like to use the data that we've set, the df data. And then we are setting our aesthetics. And we're saying here that we want our x-axis to be extra. So how many extra hours of sleep did each individual get? And then we're saying down here, we would like it to please be a histogram with geom histogram. And this time, this is an extra one. So this is facet grid by group. So we're generating two separate histograms. So they're going to be side by side. And that's what this facet grid does, is it puts those two histograms side by side. So if we were to run this, takes a second, considering its options, we get this. So we can see, here's the histogram for group 1, here's the histogram for group 2. So that's why we used facet grid, is to see this difference. And we can see the data look, mostly normally distributed. Again, with a low N, it's a little bit more challenging to tell, but that's one way of looking at it. We could put them both in the same plot, but I personally don't think it's as clear visually to be able to see what's going on. But if you wanted to do that, you, again, would start with your ggplot line, define your data, define that you want the x-axis to be how many extra hours of sleep, and then you would say fill equals group. And that's just saying, please make each group a different color. So since we have two different groups, we will have two different colors. Then we'll go down to our geom histogram line. This time we have some extra information. So we want position to be identity, so, counting, and alpha or transparency to be 0.4. So if we run this one and give it a second to pop up, then both of the histograms are going to be on the same plot. So rather than being side by side, now we see, okay, group 1 is in pink here, and group 2 is in blue. But where they overlap is like this darker color. So it's not as clear, I don't think, but perhaps there are other applications where you would want both of them on the same graph. So you can do it either way. Another way of looking at normality is using a QQ plot and then a detrended QQ plot. And to do that, we will need to add or to call QQ plotter. So this is an add-on to ggplot. So we'll call that. And then here is the code to make a QQ plot, again, by group. So we start with our ggplot call right here. We say, this is what we'd like our data to be, please. The data is the DF. And we have a mapping call right here. And so we say, for our aesthetics, that the sample data is this extra column. And then this color and fill by group is saying we would like each group to please be a different color. And then these lines here, the stat QQ, that's why we had to call QQ plotter. So that's what's making those, that's what this is calling. So the QQ band right here is saying this is what our confidence interval is. This is kind of transparency here. And this is the band type we would like to use. The QQ line right here is the line going through the QQ plot. So with a QQ plot, you'd like your dots to line up on this line. And this is saying what type of line that we'd like to use. And so identity equals true means please use this line as the reference to make those confidence bands. So those 95% confidence bands are going to be using that identity line to surround as like their point of reference. And then here is a stat QQ plot, or stat QQ point, and color equals black is just saying the data points that you're going to plot, make them be black. If you wanted different color data points, you could change the color right here. We're going to do a facet wrap. So again, a separate graph or a separate QQ plot per group. So we're saying facet wrap. We would like separate ones by group, please. And scales equals free just means that the axes can vary per group. They probably will not for this just because they're so similar. But if they were like very vastly different, scales equals free means that your axes could differ. This is a labeling call. And so we're saying for labels, so labs, we would like our X label, please, to say theoretical quantiles. And we would like our Y label to say sample quantiles. Then lastly, we have a theme call. So theme underscore BW is just addressing what the background of the graph looks like, what grid lines you can see, etc. So here we'll run it. And this is what we get right here. So for group 1, for group 2, and what we're looking for is for our dots to kind of line up along this line here, but to certainly be within these bands. And what we can see for each of these is that the dots do fall definitely within the bands and relatively neatly along the line. So excellent. We can also do a detrended QQ plot. And with this, all we did is for all of these stat QQ lines, we added detrend equals true. That's the only difference. All the rest of the code is going to be the same. So if we were to run this one, give it a second, we see this. So this is, again, kind of looking at the normality and how far off it is from what we might expect. And so again, we would really like it to line up against these lines right here. For the most part, sort of, they do. They are definitely falling within these 95% bands. So we're pretty happy. The other thing that we need to check, since it's an independent samples t-test, is the homogeneity of variance assumption. And so to do this, we can perform a Levene's test, or we can perform a Brown-Forsyth test. Both of them are going to come from the car package. So we will first call this package by doing the library car. We can see some of the output down here is just saying that some of the functions contained within this package are also in others, and so it's masking it. And so for both the Levene's test and the Brown-Forsyth test use the exact same function. So they both have the Levene test function, but here's where we're going to differentiate them. So center equals mean will give us the Levene's test. Center equals median will give us the Brown-Forsyth test. And we'll save these as objects just so we can print them later. So to start, we'll use the Levene's test function, and we'll put in a formula. So we're saying extra being the dependent variable, and we want it by the grouping variable. This is our data. And again, since we said center equals mean, it's going to be a Levene's test. So we'll run that. And then we can perform a Brown-Forsyth test the exact same way. So it's all the same. The formula, the function, formula, data, this time center equals median for the Brown-Forsyth. We'll do that. And then we can print both of these. And so what you see here, here's our Levene's test. F statistics, p-value right there. So testing for homogeneity of variance, not significantly different. If we did a Brown-Forsyth test, this is our output here, F statistic and p-value, indicating that we failed to reject the null that the variances are the same, meeting the assumption of homogeneity of variance. So that's good. We can proceed on with our test. So we can now run the independent samples t-test. We'll again use the t-test function. This is just in base R, so we don't have to call any kind of packaging. We give it our formula. So again, here is our dependent variable. This is what we are looking at, and this is our grouping variable, our independent variable. And then data, we're defining that. And here we're saying that our variances are equal. So that's one of the reasons that we performed this up here. Had these been significant, so if p had been less than 0.05, we would put variance equals false, so they were not equal. But we can run this, and here's our output. It says we ran a 2-sample t-test. This is our data, so it's kind of repeating our formula back to us. Here's our t-statistic, our degrees of freedom, and our p-value. So we see that our p-value is larger than 0.05, and if we look down here at our confidence interval, our 95% confidence interval, we see that it includes 0. So here we would, again, fail to reject the null hypothesis that there is a difference in means between group 1 and group 2. We can calculate an effect size as well for this, and we can either do it by hand or we can do it using the effect size package. To do it by hand, it looks a little bit scary here, but this is defining our variables. And that will ultimately make our life a lot easier, because what you'll be able to do is just copy this portion, put in the requested information, and then run this down here. So a little bit of setup, well worth your while. So what we have is variables for group 1, variables for group 2. So we have our in for each. And if we scroll back up right there to our describe by output. So we need our in for each group. We can get that right here. We need the standard deviation for each group, which we find right here. And we need the mean for each group, which we find right here. So we define all these. So we're saying that in 1, so the in for group 1 is 10. Like we're just setting values. So if we do all this, we see some values pop up over here. So the in for group 1 is 10. The in for group 2 is 10. Standard deviations and means. So these just are holding values. The first thing that we'll need to do is calculate a pooled variance. So here's the formula for calculating a pooled variance, and we're saying that's going to be the object SP. So if we run that, we see that we get this. So the pooled variance is 3.6. And then we can calculate Cohen's d. So ABS is absolute value. So we're saying we'd like the absolute value of the mean of group 1 minus the mean of group 2. And it's going over the square root of the pooled variance. So that's why we had to calculate that up here. And if we run that and assign it to an object, and we can print that and see that the effect size is 0.83. So that's how you would calculate it by hand. Or we can calculate it using a package. Again, the effect size package. So we'd call that first, and then ask it for Cohen's d. And since it doesn't have an absolute value, it's negative 0.83, but equal to the one that we calculated. So large effect size, non-significant t-test, and that is information that we would include in a write-up.